Welcome back to ECE 442-542. We're trying to make this the review session for exam number 2. And the process we've already gone over, so I won't spend a lot of time. The blue indicates what is allowed. The red is what is not allowed during the exam. And essentially, the exam is covering 2 homework assignments. Homework number 3 is dealing with the region of convergence and the inverse Z transform. And homework number 4 is discrete equivalence. And that's the material that you will be responsible for on Wednesday for exam number 2. And really it's partway through, or it's since the previous exam material stopping point and halfway through today's lecture that we had earlier today. Now, with respect to the region of convergence, the left-handed side, the right-handed side, in the time domain, the region of convergence is this location in the z-plane. The left-sided, right-sided, two-sided, that's the time domain behavior. I thought of something that maybe it will help, maybe it won't, but oh boy, here is what I thought might, and the region of convergence needs to be connected. Is that clear, what I mean by that? But now if we go from the definition, let me even make this, since the screen is really big, I think you can probably still see that on your screen, and it's not too bad in terms of resolution. I need to wake up, so I'm going to walk around a little bit and talk about what I've tried to display here. Wow, these projectors look different, don't they? Just an observation. They're not really 0 and 1, they're sort of... We have the definition of the z-transform, that's this infinite sum, and we start from this tail, x of minus a zillion, z to the plus zillion, etc., up to x at time n equal minus 2. The little x's in red on the right are the time domain waveform values of the waveform x. And maybe it's helpful to see that when you have a left-sided sequence, then your region of convergence is inner or inside your poles. That's what I'm trying to indicate with this black curly brace above the left side of this expansion of the z-transform. That if you allowed for, let's say, z to equal 0, and the blue shaded area are those values of z that allow this infinite expansion to exist. And if you picked a convenient value of z in this upper left region of convergence, let's say the origin at z equals 0, then I hope it's clear that those terms on the right would cause that capital X of z to go unbounded or to be non-existent, because you're now dividing by z and you would be dividing by 0. And that's why this inner region of convergence is really associated with this left-sided time domain behavior. If we had our region of convergence being unbounded, I used that term in a homework assignment, and that was confusing because you were associating unbounded, the word, with time domain behavior, but you can use that relative to the z-plane space as being unbounded. Now if you have an unbounded region of convergence, I'm meaning now you're going off to infinity as z increases. And that's the upper right-hand region of convergence, or this outer And notice that the poles are never hopefully located in the region of convergences. They are always bounding the region of convergence, but they're not inside the region of convergence. And the region of convergence, these shaded regions, are connected. Meaning you can't have sort of the top ones combined. I'm going to fall over, aren't I, walking around? Have too many things to trip on. Then that would be a disconnected region of convergence. But the upper right hand, now I hope you can see that if you picked a convenient value for z, a big Z, then those terms on the left have to be 0 in the time sequence, those x with arguments of negative n's, those have to be 0 in order for that capital X of z to be well behaved or to be bounded. Then you can have both sides of this expansion present in the expansion with an annular region of convergence. Now I hope, sort of with this picture, if that's even in your notes, which you could put this in your notes, if you just look at the 3 possible cases for the region of convergence, you should be able to very quickly know what region of indices, n's, are valid. Now if you have an unbounded region of convergence, what n's are you looking at? Negative, non-negative, or all n's? If you have an unbounded region of convergence. Non-negative. You're in the upper right picture. Whether your time sequence is bounded or unbounded is another issue. Is that clear? You can figure out what kind of side you have in terms of your sequence, independent of whether it's a bounded or unbounded waveform in time. That's what I want you to make sure you're clear on. Meaning, if we look at whether or not, can I now back, I'm feeling like I can't write that small. Who knows if this will print out very well, but we'll worry about that later. The time domain behavior, whether it's bounded or unbounded, whether your response is bounded or unbounded, a bounded or unbounded response depends on the modulus of the mode and the time index window. The modulus of the mode is just the distance away from the origin, is the modulus, the magnitude of your poles. The modes are governed by your poles. For example, if we now said we have non-negative time indices, do you already see the region of convergence associated with this? It's the upper right one in our earlier picture. That's the region of convergence associated with non-negative time indices. Suppose that the mode is such that the modulus is less than 1, and with non-negative time indices, that's within greater than or equal to 0. What do we know about the bounded behavior of that response? Is it bounded or unbounded? Is it clear that it's bounded? You now are taking this modulus r, the magnitude of your mode, and raising it to non-negative values of n. And since that modulus is less than 1, you have a bounded response. If you still have non-negative time indices and your poles happen to be, or some of them, it just takes one to have a magnitude bigger than 1, now you have just the opposite behavior. Now you have an unbounded response. Where's your region of convergence for this second case? It has to be outside all of your poles, and you have at least one pole that has a modulus outside the unit circle. Your region of convergence is unbounded, but it's not containing the unit circle, because your modulus of one of the modes, at least one of the modes, is outside the unit circle. And that gives you this unbounded response. Questions on that? Yes? Yes, so now we are dealing with linear time invariant systems, and so our transform expressions are going to be ratios of polynomials of z, always in this class. We're not going to get too out there in terms of systems. We want to be able to play with reasonable systems, and linear time invariant systems actually opens up a pretty good set of systems to play with. And if we have those, then we have these polynomials in the numerator and denominator that are functions of z, or powers of z. Did that answer your question? I'm not sure I repeated the question, but the question I think was, are we always going to have polynomials of z in the denominator? For those listening. I don't think we have the entire class sitting here, and we also have some remote students. So hopefully this is being recorded. Any other questions? Yes. Yes, so we've been calling causal and right-sided the same thing. We're now saying, and most of when we're talking about region of convergence, then we're dealing with signals, typically. But if we start talking about systems, then we are usually thinking about a causal behaving system, which now means that we're always in the upper right hand with respect to our region of convergence in systems. That's why we can specialize the stability argument always having poles inside the unit circle. Because we can have bounded signals with poles outside the unit circle if we have time indices that are maybe not right-sided. Let me sit down carefully and look at the other case. This was for non-negative time indices. If we had negative time indices, or left-sided sequences, now you should already see the region of convergence. Now if you looked at having a mode, or all of the modes with, or I'm sorry, at least one of these modes with r less than 1, then what kind of time response behavior are you going to have? Bounded or unbounded? This is now an unbounded response. Now you're raising something that's less than 1 to a negative power, and that's going to go unbounded as that number continues to get more and more negative. Okay? And likewise, if we have something that's bigger than 1, now let's say that we now have the modulus with all of them outside 1. The region of convergence is interior to all of these since we have a negative time index. The region of convergence actually contains the unit circle, and we now have a bounded response. Questions on region of convergence, right-sided, left-sided, two-sided, and time domain behavior being bounded or unbounded? You should be getting that. And so that it's very quick for you to sort of decide what you have for a given collection of poles and region of convergence. The reason why we're interested in the region of convergence, that allows us now to determine uniquely the inverse Z transform. And I just said that we might have y of z being some ratio of polynomials of z. If you're trying to do an inverse Z transform, which of these or what part of capital Y of z do you probably want to focus on if you're trying to take the inverse? Is there any part of this, and I haven't shown any of it, we have a numerator, we have a denominator, do we need to worry about both? Yes, but which one do we really focus on? Probably the denominator. You probably want to check the roots of that denominator. And that's now going to give you a feel for what you might see as far as the response behavior or how to deal with this. If you have real roots to your denominator, what kind of time domain structure do you have? Oscillatory, sinusoidal, and it's going to be exponential, which it could be either bounded or unbounded, but it's exponential. So here is your exponential response structure when you have real modes. If you have complex roots in your denominator expression, then we have exponentially damped. Sinusoidal response structure. And sinusoidal, I'm meaning that contains both sine and cosine structure. Suppose I gave you the following. Maybe I presented you with y of z is equal to z over, let's say, z squared minus 0.75z plus 0.125. And now, if that's all I gave you, you couldn't uniquely identify the little y of n. You could have a right-sided or left-sided based on this information. But if I now say, suppose the region of convergence is such that this converges, or y of z is well defined as long as the magnitude of z is bigger than 1/2. Those values of z allow that z transform expansion to be true. Now, just as a heads up, I may give you a 4th order or 5th order or 6th order capital Y of z, meaning the denominator could be 2nd order, 4th order, 5th order, 6th order, but I'll try to keep those factored into quadratic factors, meaning you only have to know the quadratic formula. But if you do find the roots using the quadratic formula, if they don't jump out at you, they might be real or complex roots. Can you see what these roots are by inspection? You know their product needed to be 0.125 or 1/8, and you knew their sum needed to be minus 0.75 or minus 3/4. So those, you now have 2 real roots. What would you do to find the actual solution to this? Would you expand capital Y of z, or would you do something else? It's usually easier to force a z in your answer if you do the partial fraction expansion of y of z over z, so that now you have, let's say, an a1 z minus 1/2 plus an a sub 2 z minus 1/4. You can solve for a1 and a2 and end up with y of n being 4 times 1/2 to the n minus 4 1/4 to the n for what values of n? And how do you know the values of n? Is it clear what I'm asking or trying to have you find? This is not quite a complete solution, is it? You need to tell me what values of n are valid. And that's determinable by knowing the region of convergence and the relationship between right-sided, left-sided, two-sided in the region of convergence. And here we had what kind of region of convergence? This corresponds to right-sided, doesn't it, or non-negative indices. This is now an unbounded region of convergence. The poles are interior to that region of convergence, and you now know n is greater than or equal to 0. Is y of n bounded or unbounded? Your region of convergence is every z beyond 1/2. That contains the unit circle, and you could answer that by just looking at the time domain behavior of this expression. Just plug in different values of n, and you can see that those are collapsing as n gets bigger. Suppose we now looked at y of z equaling z times z minus 3/4 over z squared minus 0.5z plus 0.625. Is this enough information to find a unique little y of n? What else do you need if you want to find a unique y of n? You need the region of convergence, don't you? Suppose I tell you that the magnitude of z is bigger than the square root of 0.625. Now, even if you were looking for partial credit and you were out of time, could you tell me something about your little y of n? You could now tell me at least the flavor of those n's, right? They're either negative, non-negative, or both. And what flavor are they? Based on that region of convergence is unbounded. We know that this corresponds to non-negative indices. And if you now factor this, or find the roots, you'll find that this is now z minus 1/4 squared plus 3/4 squared. Which means that, what do you have for poles? If you tried to find the value of z that caused that denominator to vanish, it would vanish for z equal to 1/4 plus and minus j. Boy. 3/4. And now you can find the distance that is away from the origin. Or that's now the square root of 10/16, or the square root of 5/8, which is this 0.625 that we had before. Square root of that is now this 0.7906. Now our region of convergence is beyond 0.8, roughly. So we now know the distance our poles are away from the origin in the z-plane. We can also find the angle of those poles. Let's say the one with the positive angle, or the pole in the first quadrant. That's now the inverse tangent of the imaginary piece over the real piece, which is now the inverse tangent of 3. Which is 71.56 degrees. You now know those poles are in the first and fourth quadrant. The first quadrant, it's a distance roughly 0.8 away from the origin at an angle of 71.56. And that's the angle, that 71.56, that we now associate with theta sub d, the angle in the z-plane. And now you could, what kind of a response are you expecting? If you were quickly trying to gain partial credit, what would you do? What do you know structurally is happening in the time domain? It's an exponentially damped sine and cosine, isn't it? It's damped because your magnitude is less than 1, and the frequency is related to this imaginary piece. You could find this answer by looking at y of z over z and expanding that, and if you keep this in terms of complex numbers, you have z minus r e to the j theta sub d plus k1 star over z minus r e to the minus j theta sub d. Where this left-hand side, y of z over z, is now z minus 3/4 over the product of those two complex pole factors. Yes? Because now we are going to end up with, if you didn't divide by z, the partial fraction expansion coefficients wouldn't have a z in there, and most of your tables have a z in the numerator. This preserves that when we find K1 and K1 star. So the question was, why are we dividing by z in y of z over z to begin with? We want to now, because we are doing this partial fraction expansion in terms of z and not z to the minus 1. Some tables you might see this in terms of z to the minus 1, then you maybe don't have to worry about this division. We're now keeping this because we're sort of in this controls scenario. We are dealing with z's and not z to the minus 1s. We now want to keep it such that when we do find the K1 and the K1 star, we can now solve back for capital Y of z, and that z will appear in the numerator. We'll have a z, K1z over z minus a complex number, and we know how to inverse z transform that expression. K1 will in general be a complex number. And we can find K1, and if we find K1, we don't have to find or solve for K1 star, because it's just the conjugate of K1. But K1 is now z minus 3/4. That's the numerator, since we've divided out the z in the numerator. What's downstairs? If we're solving for K1, what have we done? We've multiplied both sides through by this factor in red. So we've isolated K1. Now the y of z over z expression, we've canceled the pole in the first quadrant, and we're only left with the pole in the fourth quadrant, which is this z minus r e to the minus j theta sub d factor. We evaluate that at the value of z that causes that red factor to vanish, which is when z is equal to r e to the j theta sub d. Or we now have r e to the j theta sub d minus 3/4 over r e to the j theta sub d minus e to the minus j theta sub d. And in general, that's some complex number. And if it's complex, then we can write K1 as a magnitude at an angle. And that's the notation that I will use. For K1, if K1 is complex, then we can find the magnitude of that complex number and the angle of that complex number. And now we can write down by inspection what little y of n is. It's 2 times the magnitude of K1, r to the n. What was r? R was this guy, the magnitude of our poles in the original transform denominator. Then we have cosine of theta sub dn, where theta sub d was the angle of our poles, plus the angle of our complex partial fraction expansion coefficient. And when was this valid? For what indices? Then we have to go back to our region of convergence. It was unbounded, which corresponds to non-negative indices. And the reason why we could immediately write down this time domain expression for y of n is we know if we don't understand where this came from, we could say, oh, it's K1 times the root to the nth power, or the mode, and the mode was RE to the J theta sub D to the N for the K1, and for the complex conjugate of K1, it was the other mode, RE to the minus J theta sub D to the N. That's by definition of that Z K1 over Z minus RE to the J theta sub D, for example. But now K1, remember, is complex. It has a it has a magnitude and an angle. We can say that we have a K1 e to the J angle of K1. And we also have R to the N e to the J theta sub dN plus the magnitude of K1 e to the J, or minus e to the J K1, since K1 star is the conjugate, R to the N e to the minus J theta sub dN. That's just applying the algebra or the math that we know relative to exponents. And if we collect like terms, we have the magnitude of K1, that's a number. R to the N, that's this exponential increase or decrease. In this case, it's a collapse since R is less than 1. And what's left over is we have e to the J theta sub dN plus the angle of K1 plus e to the minus J theta sub dN plus the angle of K1. And that should just be screaming at you as far as what that equals. If you remember Euler, and Euler would be happy if you remembered. This is just twice the cosine of that exponential argument, theta sub dN plus the angle of K1. And that's where that y of n comes from once you've found k sub 1. And a lot of your calculators can solve for that complex k sub 1 fairly easily. You now have 2 times the magnitude of K1, that 2 popping out because of these complex exponents. R to the N, depending on what size R is, tells you whether you're collapsing or expanding. And the oscillatory behavior is influenced by the angle of your poles. That was theta sub D. And then K1's angle is added in, and that was true for n greater than or equal to 0. Questions on region of convergence, inverse Z transforms. Homework 3. Homework 4 was dealing with discrete equivalence. And we really grouped those into sort of 2 different scenarios, or 2 different cases. We had systems that might actually be preceded by a hold device, and in our case we're going to go ahead and just restrict that to a 0 order hold. It's holding it constant. Then we have 0 order hold discrete equivalence versus the other scenario where maybe we do not have a system preceded by a hold device. We might have a filter, we might have a controller. Then we are in the other case where we're dealing with numerical integration or pole zero mapping. If we're dealing with the 0 order hold scenario, we can do that 2 different ways. We can do the transform approach, And remember, we derived this by basically applying a unit pulse to our system. That ended up giving us sort of this 1 over s with a delay of 1 sample period, and that then gave rise to this 1 minus z to the minus 1. Z transform in the unit step gave you this over. So now you had g of s over s. And I would recommend that you get very comfortable looking at the tables and finding these expressions that might involve g of s over s, and you might be able to do a partial fraction expansion over those to more easily identify the terms that you want in that expansion. So you could use tables containing, for example, f of s and f of z, and once you find the f of s term, then you can immediately say, oh, I know what the z transform of that is. It's in the same row of the table. And you don't have to necessarily go through that more involved process of inverse Laplace transforming, sampling, and now looking at what you have as a time sequence and finding the z transform of that time sequence. That's the transform approach. You could be asked, like on the homework, to do it via the state space approach. If you're dealing with the state space approach, then you actually end up with your system matrix in the discrete time representation being this matrix exponential e to the a, or e to the capital A, capital T. And you could maybe find that by looking at e to the capital A little t and replacing little t with capital T in the expansion, where this matrix exponential e to the capital A little t, if you're doing it by hand, you can now find that by looking at the inverse Laplace transform of Si minus A as a matrix inverted. This is now a symbolic matrix with the symbol S floating around. A is a matrix of coefficients. And you should be able to do that for a 2 by 2 A matrix. And what possible denominators are you looking at? You're now going to have a denominator, which is the determinant of Si minus A. And if it's second order, you really only have a few scenarios that might be. They could be real, both real, where they might be real and unequal. They could be real and equal, or they could be complex roots if it's a quadratic denominator. And we've just talked about how you could, well, that was in the discrete time, but I want you to be able to inverse Laplace transform those. So you should be able to find exponentials in the time domain from your real roots, or exponentially damped sines and cosines from your complex roots. And generically, you would have 4 of those to do. Since it's a 2 by 2 matrix, you would have the inverse Laplace transform of each of those elements in that 2 by 2 matrix. Once you have the matrix exponential, e to the at, you can have e to the a mu, which will allow you to find gamma, which is this integral from 0 to t, e to the a eta B d eta. And as I said before, if you have one input and two state variables, what's B dimensionally? That's your input matrix. What are the dimensions of capital B? Has to be compatible with your system. It's 2 rows and 1 column. You might be at an advantage to go ahead and multiply e to the a eta by b, so that instead of having 4 integrations, you just have 2, if you have to formally do this. You could actually perform this if you're given the sampling period. You could do this numerically, where your system matrix phi, and this is now assuming that you remember what we have. We have x of n plus 1 is equal to phi x of n plus gamma u of n, y of n is equal to h x of n plus j u of n. That's the state space, either below the black dashed line or above. I just didn't write it down, but this phi matrix, if you were trying to find it numerically, is the identity plus the system matrix A, the scalar, capital T, times some new matrix psi that we've defined in a lesson that I gave offline. It's available on the D2L website. And the input matrix gamma also utilizes that psi. It now has psi t times b, where psi you can now find numerically by this nested set of multiplications and additions of matrices. Meaning you pick a number, and on an exam you wouldn't want to pick a very big number, but numerically, if you were working this, maybe in reality, you might pick a number 11, for example, and now nest this up based on 11 different terms. But you might say, oh, I'm not going to do that much. Let me do 5. So you might say, there's A, your continuous time system matrix. You scale it by t, if that's given or you have to find it, and divide it by 5. That's pretty easy to do. You're just scaling A by t over 5. So now that result is what size if A is 2 by 2. It's still a 2 by 2. You've just scaled all 4 entries by a capital T over 5. Then you add to that, I'm going to run out of room, the identity matrix. Then you hit that with AT over 4. You add an identity to that. So you have an AT over 4 scale, that's a 2 by 2, scaling another 2 by 2, and you add another identity. Like I said, I'm going to run out of room. I shouldn't have started with 5. You now hit that with AT over 3. Add an identity to that. Do you see how this is nested or growing? Then I haven't yet run out of colors, but I'm running out of room, so let me erase that. I now scale that by AT over 2, and I now add that to I, and that's now my psi. So you need to pick a number, and then you sort of build from the inside out once you've picked that number. And you could put this into a loop if you were programming this, if you really had to do this seriously. But on an exam, you could probably pick 4 and build out from 4. Then you have AT over 4 plus I, multiply that on the left by AT over 3, add I, multiply that by AT over 2, and you're pretty much done. There's your psi. You plug that in here, and you've got phi and gamma. Yes? The question was on the exam, am I going to give you the method to use, or do we have to choose? And the question was, if we have to choose, which one is faster? Let's move on. So I may not tell you, and you may have to just pick what you feel most comfortable with. One may be easier for one student, and one method might be easier for another student. So that's why I don't really want to say which way, because somebody might really be into inverse Laplace transforming, and they can pretty quickly do this. And it depends on the structure of A and what you have. It might be fairly straightforward to do. And somebody else might say, that makes me nervous. Let me just do this numerically. Or I might say, do it by hand and not numerically. So you need to be capable or know how to approach both options in this zero order hold equivalent. If you, I'm not sure I answered your question, but then you can also do the numerical integration approach, which I think was problem 5 on homework 4. Is that true? One of these? Well, if you did it in the state space, I'm getting ahead of myself. Let's talk about the transform case first. We looked at 3 different possible ways of numerically integrating a waveform. You could do the forward approach, and I hope you sort of have a visual of what that represents in terms of the picture of your signal that you're integrating. That then boils down to a Z expression that you then equate with S if you wanted to then convert from a continuous time to a discrete time of Z minus 1 over T. Everywhere you have an S, you replace it with Z minus 1 over T. If you had an S cubed, you would cube this expression, Z minus 1 over T. You could be asked to do the backward rule in the numerical integration approach. Then you have Z minus 1 over TZ, or using the MATLAB terminology, you could be asked to do the Tustin, or the bilinear, or the trapezoidal, and then you're dealing with Z minus 1 over T, and then it's sort of this Z plus 1 over 2, or you now have this 2 over T, Z minus 1 over Z plus 1. And you should be able to use this to convert some continuous time transfer function, meaning an S domain expression, into a Z domain equivalent. Question? So the question, I didn't quite hear it. I went from what? So in the homework, I think I asked you to do a zero order hold equivalent of some mechanical system. Then that's kind of in the previous discrete equivalent, but you could then have an A matrix, a B matrix, and a C matrix, and a D matrix, depending on your system. Meaning, if you now had some block diagram, I guess I can go back with my capabilities. I now have this scenario. I think what was asked is what would happen. Oh, this is nice, isn't it? Sorry, you can get out your glue and scissors and cut and paste. But you might be given something like this. Is this what you're asking? You might have to start with something like that. Then you could decide how you want to label that, but then our strategy is to label the outputs of the integrators as state variables, and now you have x1 prime and x2 prime in terms of x1, x2, and inputs. And this will now produce an A matrix and a B matrix, and once you have an A matrix and a B matrix, you can plug them into these formulas that we've developed. Does that help? So that's how you could start from a physical system, which might be indicated or given in the form of an all-integrator block diagram, and it may not be labeled. So you would then be forced to label it, but just label the outputs of the integrators as state variables. Then you have your A matrix, your B matrix, your C matrix, and your maybe direct feed-through matrix. Do you have a direct feed-through matrix in this system? There's no direct connection from the input U to the output Y. Your direct feed-through matrix and your output is 0 in this case. And your output matrix looks like that. And your A matrix, do I dare do this? X1 prime is just minus 3 times x sub 2, and x2 prime is minus 4, 0. B is now whatever is making up x1 prime is 6, and x2 prime is 5, and there are your ABC. Now we've set our ABCs, we can move on. That somebody else might label it differently. They may have different A, B's, and C's, but then I would have to be basically grading two equivalent solutions. They may not give you the exact same answer, but they would be equivalent dynamically. Where was I? So we were on the transform approach of numerical integration. If you did the state space formulation, we tried to step our way through that in the last lecture. Not this tonight, but last Wednesday. And when I was thinking through that, I thought, well, maybe that seemed like it was coming from outer space. So I thought, let me try to give you another way of visualizing what we were stepping through. So here's a very quick derivation of the backward rule numerical integration for a state space representation. We're starting at home and we're finishing at the sun, whatever that means. Well, that means we wanted to start with x dot equal ax plus b e, I think was our input. U is equal to cx plus de, meaning we were starting here on the left. Do you see the house? In the blue, in the time domain, continuous time setting, and we wanted to end up down here with some state space representation. One way of thinking about this is to try to keep track of what you actually were doing, and we sort of are moving back and forth between time domain, frequency domain, and continuous time and discrete. So here's a way of thinking about that derivation that we did on Wednesday. We start continuous time, time domain. Input is E, output is U. We immediately Laplace transformed that. We moved from the time domain into the frequency domain. So we've switched columns. That allowed us to introduce this S variable. And if we're doing the backward rule, we know what to replace S with. It's going to be replaced with z minus 1 over tz. We're still in the frequency domain. We've just now transitioned from continuous time to discrete by that discrete approximation of replacing s with z, this z expression. Is it clear where that first step came from, or we've now really done two steps? And this maybe gives you a better visual of, well, that was kind of a convoluted, well, I shouldn't use that word, but an interesting derivation. Well, now maybe if you see it in this structure, maybe it will make more sense, is my hope. Now it's a visual depiction of this derivation. We start continuous time in the blue. We move across from the time domain to the frequency domain just by Laplace transforming those state equations. That allows us now to have this S variable floating around, and capital X of S and capital E of S, those are really just variables. The argument is not so important. It's just a label. And when we go from continuous time to discrete, we just need another label, and we're calling that's a function of Z. So that now we have an integrator, let's say, and now we have in the analog, and we have an integrator in the discrete time. But here we're replacing S with a Z expression based on the backward rule. Then we simply stay in that same column by performing some algebra. We're still in the frequency domain, but we just manipulate what we have. We multiply things out, and then we go back into the time domain by inverse Z transforming. Since inverse Z transforming is trivial when all our operator is just Z. That's just an advance. Now we've moved back into the time domain column, and it's maybe a little bit messed up because I ran out of space and had to put the one line on sort of a two-line picture. But then the big thing was to define this new state variable, W. But once we defined that, boom, the state space representation just falls right out. The big thing really was understanding or realizing that our state variable in the state space representation of our end result didn't have to be consistent with the state variable that we started with. It didn't have to be X. It actually was W. But if we wanted X, we know that the way that we defined our W allows us to easily go back if we need our state X. We know little x of n is just W of n plus 1, and we can generate W of n plus 1 from our sun expression. the blue, I'm sorry, yeah, the blue boxed red system, where the phi, our system matrix, the gamma, the H, and the J are all determined once we have the system matrix A. So if I now gave you an all integrator block diagram and I said, give me a state space discrete equivalent using the backward rule, it wouldn't be that hard, would it? Just some manipulation, some mathematical manipulation. You'd have to do a matrix inverse, but on an exam, if you're pressed for time, I would just write it down. I would say, here's A, it equals this. And I need phi, capital Phi, that's I minus AT inverse. And maybe you need to find T. Find that before you compute the inverse, and I wouldn't even mess with the inverse if I were you. I would move on. But that shows me that given the time, you could determine the actual capital Phi, the gamma, the etc. Is that clear? And you can do the same thing, and I think I've provided you with an explanation. The forward rule strategy is not nearly as involved, but you do jump into the frequency domain, you do the substitution, then you jump back, and then you're basically done. Yes? So now I think the question is, can you go from house down to sun by staying in the left column? If you can do the, but there we were really doing the integration. Here you have a differentiation in the time domain. So now what does the integration look like in terms of a derivative? So if you can make that connection, then you might be able to find the relationship, but I'm thinking that's not going to be so easy. So we should look at that and see if you get a similar result. Okay? So that's now one class of numerical integration. Well, or I should say scenario number one with discrete equivalence. The last one that we talked about was pole zero mapping that you need to be comfortable with. And here, the mapping part is pretty easy, pretty straightforward. Pole factors, zero factors with this relationship. Z is equal to e to the st. What you need to key in on is the pole zero excess. What does that allow you to do? Why is the pole zero excess important? That gives you your number of zeros at infinity, and whether or not you want to force a delay in your implementation, you might say, let me pick one fewer zeros at infinity relative to this z plus 1 factor, like we talked about in today's class, and get the MATLAB result. Then you can match gains once you've put all of the factors and the z plus 1 factors in, which allows you now to find g of z from g of s. And matching gains depends on what kind of g of s you have. For example, if g of s, let's say now maybe the gain at DC is bounded, then what do you want to do? Then you want to match at DC. And that now says, and where G of Z is determined except for maybe an unknown gain K or K bar. And you can now find K bar that way. And if you wanted to look at maybe the gain, let's say at DC is equal to 0, and the gain at infinity is bounded, then what do you do? If this is associated with G of Z, or I'm sorry, G of S. Then it's not going to do you much good to try to evaluate it at S equals 0, is it? If it's going to 0 at DC. But now you might match at infinity. Where now you have G of S at, let's say, S going off to infinity is equal to G of Z at Z equal to -1. And if you have another case, let's say that you now knew that G, let's say G of S, looked like that, for example. Now what would you do? Your gain at DC might be 0. Your gain at infinity might be 0. Now you go, uh-oh. But you can still pick a particular frequency, maybe something, if it is fairly flat in the pass band, this is now a band pass filter, you could match at some frequency omega, and now your Z is equal to e to the st, and you know what S is, it's some j omega value. And you know what the omega is, it's between those two bends in your bandpass behavior. Questions for exam number 2? More questions, I should say. We've had a few questions tonight, haven't we? Maybe. Yes. So now can I explain the subtracting of zeros at infinity? Now if we are doing the pole zero mapping, and let's say that you had some G of S that was, let's say, S minus 1/2 squared plus 1/4 squared. I'm really not being very creative, am I? Actually, I don't want this. What would this system be? Be unstable, wouldn't it? So let me do that. I want it to have poles in the negative plane, and now let's say that this ended up being 4 or something. How many zeros at infinity do I have? Now, if I looked at G of Z, my denominator is going to be some Z squared. And if I had 2 zeros at infinity, if I did it the generic way, I would say if I map both of those to a value of Z equal to 1, then I would have something like that. And I would probably be, this is some low pass behavior, isn't it? At DC, I have some value, and then at higher frequencies, it starts to roll off. They're not very high frequencies with my small values in the denominator, but if, and what's this going to give me? If you look at what this is, if we say G of Z is now, let's say U of Z over E of Z, and if we multiplied this by a z to the minus 2, the numerator now is z squared plus 2z plus 1. When I multiply it out, I now have 2 delays, but do you see that the u and the e, when I go into the time domain, my input at the present time will need to be known in order to generate the output at the present time. Meaning this is going to translate into u of n equal to something u of n minus 1 plus a something u of n minus 2 plus something e to the n plus a something e to the n minus 1 plus a something e to the n minus 2. And you may not like the fact that you are generating the present or the input now, I'm sorry, the output now with the input now. You may not be comfortable with doing that. You may want to say, I don't want to wait very long before when n comes, I want to immediately put something out to my system. And if that's the case, then you say, let me design this to where I only have e to the n minus 1, e to the n minus 2, and previous e's on the right-hand side. If that's the case, then you would go back to this state and you would say, I don't want to put both of those zeros, associate those with a z plus 1 factor, those zeros at infinity. I actually want to do a g of z, whatever this was. Did I have an alpha and an alpha 2? Now I have a k hat z plus 1. I have now done, instead of having a 2, I've actually reduced it by 1. And that now gives me, when I multiply by my 1, which is z to the minus 1 over z, I'm sorry, z to the minus 2 over z to the minus 2, I now have 1 delay and 2 delays in my input, creating the output now. And that's why we might want to force one of these zeros at infinity to actually be a 0 at infinity and not at z equal to minus 1. If you look at what's in red here, if I let z march off to infinity, what happens to g of z? Forget the blue for now. It's easier to just think in terms of z plus 1 over z squared. The highest powers of z dominate. I now have z over z squared. I have 1 over z. As z goes to infinity, that goes to 0. So I now have preserved 1 0 at infinity in my g of z expression. And I now haven't mapped both zeros at infinity to a factor of z plus 1. And the reason I did that is so that I would be able to not have to worry about this piece on the right-hand side. If you now go through what will happen here, you're going to end up with u of n plus u of n minus 1 plus something u of n minus 2 plus something e of n minus 1 plus something e of n minus 2. And now that e of n is not on the right-hand side. You just have to wait until now hits, and boom, you can spit out the answer because you've been able to compute the right-hand side in this time interval between n minus 1 and n. You don't have to get the input at the present time to combine it with any more terms on the right-hand side to move forward. So what? It's a Cooler equation. Well, that's up for debate. It depends on your goal or what you're wanting to do. You may want to have the input as close to now as possible, and if your computing power is quick enough, you may be able to tolerate the amount of computation delay necessary to measure E at now and then generate the output now. If that happens, like I said, in less than 10% of your sample period, you may be okay to be utilizing this expression. But it really depends on your particular situation and your implementation. If you have a slow processor, then you may want to focus on doing this. And then the coefficients, the gains will take care of themselves because you find k or k hat after you've determined the polynomial structure in the numerator and denominator. Other questions? Yes. Is h just equal to c? I believe it is, yes. So if you go back to the derivation, which I'm not sure that I even have it on my machine here, but if you go back through the derivation on D2L, you should be able to see what c and h look like relating the continuous time to the discrete time. And I believe there you are just, that's a linear equation relating the state and the input to the output. And so C is equal to H. Yes? The question was, am I reducing the accuracy of the approximation by changing the number of zeros at infinity that get mapped to the z plus 1 factor? And what I'm trying to say is your k hat has now been adjusted to account for some of that change. If you remember what happened in our example, we were averaging two inputs and scaling by the same factor, whereas before we were just taking that input and scaling by that factor. So you're using less information, and that may or may not be helpful or harmful in your particular case. It really depends on your situation, and you might want to decide which trade-off do I want to tolerate. Am I okay with a little delay in spitting out my output, or do I want to spit that output out immediately upon the instant occurring? And that may be more important than this sort of using more input information in processing that output. So it's hard to say until you look at your particular example or the particular case. I will leave it at that, and I will see you on Wednesday for exam number 2.